Okay, so we just left off with this part, so let's go ahead and keep going. The next thing I ask you to do in the second homework is to consider. Again, we're doing an analogous problem here, certainly a little different, but give you a sense of how this is running. Suppose I don't specify the value of the voltage, I don't specify the value of the resistor, and I don't specify the value of the capacitance. And the equation is still V minus I R minus Q over C equals 0. And we're just not going to substitute values in there now. So let's rearrange this again. So let's see. We'll have, we're still going to think of I as dq dt. So we're going to have a dq dt equals we'll do a V over R minus a Q over RC. And so the benefit of doing it with the numbers is that it was pretty easy to see that we had a line with negative slope. And this is the same thing. Nothing's changed. Your voltage is a positive number, your resistance is a positive number, your capacitance is a positive number. So we still have a line. The vertical intercept is V over R. Once again, we can find the equilibrium by solving when Q prime is 0. That will be over V over R minus Q over RC. So if we solve, I'll move this over, multiply by RC, we'll get Q equals VC. Right? So that's the equilibrium. And same thing if the initial charge is between 0 and VC, we have a positive Q prime. And if it's larger than that, we have a negative Q prime. All right? So we can sketch solutions just like we did a moment ago. And this is nice because we can really reveal a lot about the system without having to play with any specific numbers. Do things in general here. And sometimes folks get caught up, how do I graph VC? I don't know what it is. It's a positive number, and it's right here. You can't tell exactly where it is, and you can't make a scale, but it's greater than 0. So there it is. And once again, we can tell that if we start at 0, we're going to start very steeply and then taper off. And if we start closer, it'll be less so and less so. And the solutions are still symmetric, because starting an equal distance on either side of that equilibrium is going to give you the same derivative magnitude, increasing or decreasing. So I can still, I can still sketch solutions, easy peasy here, even if I'm just using these letters. I can tell there are no inflection points. I can tell when you're increasing or decreasing, what's the equilibrium, what's the limit of the system. These are all things that I can tell. And okay, so I do ask that here. We've sketched some solutions, and we can ask this question: what is the limit as t goes to infinity of q of t? Now this isn't a limit that I can do in the Calc 1 sense, because I don't have an equation for this. I know you guys, guys and gals, know this from physics, but if you didn't, you don't have to have the form of these, the functional form of these curves. We can tell what's happening. The limit is VC. This is the limiting charge on the capacitor when the system equilibrates. So that's pretty interesting. Now let's see. There's no analogous thing here. Okay, so now let's. I think I'll stop here, and what I want to do next is jump to a variable voltage source. So the thing we're going to do now in the next video is, what if what if this involves time? Now we won't be able to do this particular analysis, so we'll use Euler's method. So that's what will be next, and we'll do a screencast of that. I'll show you the spreadsheet. Okay.